Good morning, good afternoon, good evening to you all. Thank you to Miriam for the introduction, and thank you for joining this presentation in which I will provide an overview of OPC UA and its benefits, and I will also demonstrate how easy it can be to integrate AI-based image processing into industrial applications and environments using the OPC UA standard. This talk builds on a number of presentations available already on the IDS Vision channel. So if you haven't already watched these, then I certainly encourage you to do so as we cover the topics of artificial intelligence and edge processing in more depth. So, integrating any components into new or existing industrial systems, whether these are sensors and cameras or processing equipment or even ERP software, can be very challenging. System builders and integrators have to familiarize themselves with many different systems and communication methods to connect the components to work productively. On a device level, there are many industrial protocols that devices might communicate over, such as Profinet, Ethernet IP, EtherCAT, and a number of other proprietary TCP/IP based communications. And for machine vision systems, there is no generic interface on the application level, which means automation engineers can be limited to the choices that they can make and which devices to use based on their compatibility and whether they share the same protocols. And for each new project, one proprietary interface must be chosen, or maybe multiples, and these have to be understood and used. And this can be cost intensive, it can be time consuming, and especially if there is the need to convert information between different protocols, can provide a greater chance of errors in the system. So there is a necessity to address these challenges, and this has been addressed initially by the OPC standard and later the OPC UA standards. OPC stands for Open Platform Communication, or at least has evolved to this definition. It's been around since the mid-1990s, with the original or classic OPC standard allowing some level of manufacturer independence for the data exchange through a server-client relationship. But this still required hardware manufacturers to provide specific drivers and was based only on the Windows operating system. So this led many automation companies and system integrators to stick with the proprietary industrial protocols and standardize on specific device manufacturers and simply deal with the translation of communication between incompatible devices. But even for those that embraced the OPC standard, with increasing adoption of other platforms like Linux or Android, web architectures, cloud computing, and IoT devices, a successor became necessary. And this is where OPC UA, Universal Architecture, comes in and builds on the OPC standard. Now, it's not enough to just have a new standard, and in fact you may even ask, is there the need for another control protocol? What makes OPC UA different is that it doesn't know or standardize device-specific settings and functions. OPC UA only regulates how devices communicate. And this means that the initial setup of a device is still done via a device-specific interface. But by using OPC UA, prepared tasks or recipes and prepared configurations can be executed easily. So we can see OPC UA is well thought out, but new ways of industrial communication must always have industry backing for it to be widely adopted. So the OPC standard is managed and developed by the OPC Foundation, and this is an organization of nearly 700 members worldwide and includes some very big names in the world of automation and computing like Siemens, ABB, Rockwell, Microsoft, Beckhoff, Schneider Electric, and IDS is also a member. Stability is also crucial, and to that end OPC UA has been published as a standard, so it will be stable and available long term, and so users can be confident in its adoption. Looking at what OPC UA consists of, we have core specifications, and these are a defined way in which servers describe themselves to client devices and which information and services they offer. Servers don't need to use all of the specifications, only those that are relevant to the service or process. It contains things like data access, security models, alarms and conditions, and the publish-subscribe model, the so-called pub-sub model. And then in addition to the core specifications, there are companion specifications, which are information models developed by specific industry groups and includes things like injection molding, CNC machines, robots, RFID, and of course, machine vision. The architecture of OPC UA builds on the original server-client relationship that was introduced with OPC. An OPC UA server will respond to requests and provide data to any number of clients based on this publisher-subscriber model. This means that messages are only sent and received between devices in the network that are interested in the message, in what the message might contain. So this means it achieves excellent network efficiency. And the client server structure allows the use of any number of network topologies. The standard offers complete platform independence with respect to not just the manufacturer, but also the operating system and the programming language used. From the OS side of things, it's not limited to just Windows now, so it can work with Linux, with Android, with Mac OS, and really anything else that can work on the TCP/IP level. And the possible programming languages has been expanded similarly, opening up the possibility to develop OPC UA client software to more people. Security was an important topic from the beginning, especially important when dealing with wireless devices and cloud-based software. So authentication, authorization, and information integrity is built into the standard. And then finally, OPC UA is extremely scalable, since it can be easily integrated into not just the systems at factory floor level or production level, but also between different layers in a single business. It can also be implemented on wirelessly connected devices and cloud-based systems. And can be used across really any applications that might require data exchange. So due to the network basis, OPC UA is quickly and easily available on a large scale and easy to use, and this is all without any additional hardware requirements. Coming from the machine vision world ourselves, the machine vision companion specification is of particular importance to us at IDS. The working group is made up of the OPC Foundation and the VDMA, both of which IDS has memberships with. Plus there is global representation from machine vision and imaging organisations with the AIA, the GEA, EMVA and CMVU as advising members. The specification is relevant for any vision systems. So that's from component-based vision solutions through to embedded smart cameras, and allows basically the control of a machine vision system. And this covers the parameterization of things like camera exposure and gain, triggering control and lighting control, and that's via the configuration data management. We also have a functional module known as recipes, and this takes care of how the vision system runs. So, for example, what image processing is running on the system and the results output conditions. OPC UA also provides a generic method of transmitting results from the machine vision system. because of the huge variety in what might be configured on the system and the variety in the format of the results. The actual contents remain vendor specific and are therefore treated as black boxes. For the OPC UA user, it is not important how the device performs a task, only that it can do something and offers it for use. And this ensures that the standard is not too rigid with rules that are difficult to agree on, and that would result in longer development cycles. And any new machine vision devices and techniques can easily incorporate the standard without having to wait for another revision of the standard to be published. As an example, we can look to our own IDS NXT cameras, where we offer the possibility to perform machine vision tasks based on AI classification and object detection with the supplied vision apps and wider NXT Ocean framework, and traditional rules-based processing via the custom VApps and the Vision App Creator. As the IDS NXT cameras can run autonomously without a PC connected or a user interface, in the majority of cases there will still be the need to somehow communicate the results to a wider system, or to configure the machine vision process to work with different products, and this fits perfectly with OPC UA. Looking at this conceptually, an application engineer can use the IDS NXT cockpit software to set up the configurations and the recipes that are stored on the camera, and this can also be done via the REST API. As an example, a food packaging system may handle different products on the same line. So recipe 1 might perform object detection on sealed trays of chicken breasts to check for the right content. Recipe 2 might be checking chicken wings, and then recipe 3 may be configured to check chicken thighs. And each of these might also require a slightly different configuration to adjust for different lighting levels because of different levels of reflectivity, or for different trigger timing because the packaging may be slightly different sizes. So at runtime, the controlling system can talk directly to the camera via OPC UA to set the prepared recipes and configurations depending on the production program. And then whenever the IDS NXT camera detects that the trays do not contain the right number of products, or perhaps identifies a defect, it can signal the result to a reject mechanism directly as an event and to an ERP system that is monitoring productivity. Go further into the machine vision companion specification, we have the unified device view. And we can see the sorts of information that is available through this. So we have high-level system information like the device name, hardware and software revisions, the manufacturer and model of the device, some variable system health details like CPU load, the memory usage, or the power supply levels, and then also statistics such as images acquired, any images that have missed, and the pass-fail count for the vision processing. And this mirrors everything that is available on the NXT cockpit software interface. Okay, enough talk. Let's see a demonstration on how this looks and how to set up the recipes and configurations on the camera, and then interface via the OPC UA test platform that we have set up. And spoiler alert, it is extremely simple and very straightforward. So this is our IDS NXT cockpit software. So this is what we use to configure the camera. So first of all, we want to enable the OPC UA server vision app, and then set up the camera for the imaging side of things. So with this interface, we can set things like the exposure, the gain, the white balance settings, and any number of triggering and digital I/O options. But here we will optimize the setup so that we have a nice image, and then we select the OPC UA setup page again, and then we need to set the configuration name. So we give it something descriptive, something that maybe says what the exposure time is or anything else that it's important for the setup. And then click on Save the current configuration. And this is then stored in the camera. And we can see in our drop-down list we have another configuration that we'd previously set up. And it's much the same process for the recipe setup as well. So in this case we are using the classifier vision app, and we want to, well, we've got something set up already to classify different types of nuts. We now want to set it to classify the cookies. So we load the neural network that we want to use, and we also need to reset the search regions. So we set this for the 2 positions of the cookies in the image. We can then test and make sure that we're getting the results that we expect, and then switch back to the OPC UA interface. So again, we need to give the recipe a meaningful name. The actual vision app is already selected as classifier, and then we click on save the recipe, and we can now see that this is available along with the nut classifier in our drop-down list. And of course, if we make any mistakes or if we need to remove any legacy configurations, we can do this from this interface as well. And that's everything on the NXT side of things. To show how this then interfaces to an OPC UA client, we can use some test software which has a lot of parameterization in it. Fortunately, we only need to address a small section of it for our purposes here. So I have a connection already to the camera. This is pre-configured. And from here, we can ask the camera to report all of the available configurations and all of the available recipes. So the client software then knows what the server can do and the correct names to use when changing the recipe or the configuration. For our example, we can look at a scenario where we are currently inspecting cookies, and we want to change products to classify different type of nuts. So we can see the cookie classifier running already in the cockpit software. So we need to go to the recipe management section in our OPC UA client software. And first of all, we can query the available recipes on the camera. And then from there, we can copy the name of the nut classifier recipe, and we'll copy it to avoid any typos. And then we need to set the recipe. So we use the prepare recipe object, paste the recipe name into the required field, and then send the message to the NXT camera to load this recipe. And we can see immediately within the NXT cockpit interface that we are now using our nut classifier. We can also see the OPC UA client software receiving messages and events from the camera itself. So the camera is set up now in a software trigger mode, and as we acquire each image, we see a new event appear, and this is a result from the camera. And within this, we can see a fairly complicated looking structure, but this is essentially OPC UA based. So any OPC UA based software will understand this and be able to take this and use it for its wider purpose. So there we have it. OPC UA provides an ideal means for interfacing a wide range of industrial and non-industrial devices and systems with its optimized architecture, the platform independence, the high security and scalable scope, and the further expansion of the standards with the companion specifications opens up OPC UA to an extremely wide user base. And we at IDS think it is the perfect complement to the IDS NXT inference cameras, opening up the world of AI processing to automation engineers with little to no experience with image processing and artificial intelligence. For now, thank you very much for your time.